But yeah, so thank you all very much for having me here. I'm yeah, just really delighted to get to share some of the work that we're doing and to hear your feedback and your questions on it. Um, so with that, I'll take it away. So I guess what's always really fascinated me is the ability of people and animals to acquire rich capabilities from their experience. So you think about like, if you ever, if you have children or spend a lot of time around, young babies, or if you've seen a young like puppy or a kitten at the beginning of their life, you know that they are very incapable and they really can't do very much. But then over time, as you just watch them gain more and more experience, and of course in biology, also, bodies developing, you see that they become amazingly proficient at a wide number of skills. And even like very many animals are vastly more capable than any robots that we can develop today. And so as a computer scientist, I want to understand, what is the principles? How can we recreate this same ability to learn over time in computers and robots? And while a lot of my research is general in the sense that it's not only focused on robots, I've always been really drawn to robots. It's an important kind of application area of my work. And so just this question of how do we create embodied intelligence for the physical world, I think is just one of the greatest scientific questions that we have right now. So inspired by this, all of the work in my lab kind of falls under this big question of how can autonomous agents learn goal-directed behaviors from experience. This question is very kind of well aligned with the goal of the field of reinforcement learning. So most of the work we do, is contributions to reinforcement learning and robot learning work. So I like to divide all of the different projects that we do into three broad categories. So the first thrust of the work that we think about is both RL is how do we make RL algorithms that can be deployed in real world problems. So some of this is very like fundamental algorithmic work, some of it even like more kind of RL closer to RL theory work. But thinking about just like fundamental problems that are like kind of always present, like how do we learn with a limited number of actions in a given context? We also think about like more pragmatic approaches to making RL practical. So things like sim to real and data augmentation, techniques which allow us to use today's best RL algorithms, but on problems where they couldn't be directly applied. Another big topic area that I think a lot about is trustworthy RL. So as the field of RL is becoming more and more capable of actually real applications that potentially have great real world impact, we have to have confidence that those decisions are going to lead to good outcomes for people and whatever the application is. So I think a lot about how we can validate learned behaviors before they are deployed. And then the final research thrust in my group is thinking about challenge problems in reinforcement learning. So there's a lot of, the field of RL for both good and bad as there's many standard benchmarks that are used to measure progress. And oftentimes when you take an algorithm which is successful in those benchmarks and you try to apply it to some new problem and you see that things don't work quite as well. So I think it's really important to be like saying, well, what are some, potential application areas or just sequential decision-making problems where people haven't looked at RL, and saying, how can we apply reinforcement learning there? And then, kind of based on our experience, this usually raises kind of new fundamental research questions. So some of the things that I've worked on in the past is, RL and some problems motivated by network systems, robotics, of course, and control of transportation systems, as well as autonomous driving. Um, so that's all of my work in a nutshell. I'm going to try to kind of talk a little bit about each one of these without going into a ton of detail on one specific work, but try to tell you about a bunch of different projects that have happened in our group. I think many in this seminar are already kind of familiar with the general setup for reinforcement learning, but just here's a chance for me to say how I'm modeling the world, and just for anyone who's not familiar with this to get up to speed with it. But we have this general setting where we have an agent interacting with an unknown environment. Agent takes actions. Actions affect both the state of the environment and the reward that the agent gets. Our goal, when we say kind of learning to act through experience, is that we want this agent to start with kind of no ability to know what actions will give it the most reward, and over time try out different actions and learn a policy, which is a mapping from states to actions that will maximize how much reward the agent gets over time. So as I think many of you know, this is an incredibly general formalism applicable to robotics, but also applicable to many other domains as well. So now what I'm going to talk about today is three kind of recent works in the group. So the first thing that I'm going to start with is a case study in reinforcement learning for the domain of robot soccer. So this is going to be a case study in a fun but also very challenging domain for modern reinforcement learning algorithms. And of course, some of the lessons from this, applying RL in this domain are going to be specific to robot soccer, but I think a lot of them are very general, and they're also, lessons that are observed in other applied RL success stories as well. After talking about this first part, I'm going to talk a bit about some of our work on how we can develop trustworthy reinforcement learning. And then finally, as time permits, I'm going to talk about how we can develop agents that learn how to balance both the amount of reasoning they have to do, as well as the demands of acting in real-time systems. So let's dive into the first part. Okay, so here's a video of a robot soccer game from RoboCup. This was in the 2024 competition. So if you're not familiar, RoboCup is an international robot soccer competition with a long-standing goal of that a team of robots should be able to defeat a team of human players, in fact, the best human players, by the year 2050. So I think soccer is a really great domain for studying and kind of stressing robotics research. So it's a real-time domain, and it's on a physical system. And the robots, everything must run on board the robots, which means compute is limited here in terms of what you can run. So the environment is also adversarial. So of course, there's other agents that are trying to mess you up. It's very dynamic. So things are not going to be where they are from one time instance to another. Everything is constantly changing. And it's very partially observable. And so this is, of course, both because of the robot's limited view, but also because the limitations of the onboard compute mean that, the most powerful perception methods cannot necessarily be used. And you have to think about these real-time constraints. And so it's not uncommon for robots to have a high degree of uncertainty about the world. And then the other challenge that this domain introduces is that the robots must be fully autonomous. So there can be no human intervention once these competitions start. And this means you need a high degree of reliability required for competition. So this is really particularly challenging for learning-based methods. And in particular, I think in recent years, there's been a number of, very high-profile demonstrations of robots engaged in soccer play. So for instance, Google DeepMind had some really cool work of doing kind of end-to-end soccer learning. And that was really impressive work. But, it doesn't, if you watch the videos, you'd see the robots would get stuck in situations and there would have to be some intervention from a person to get them playing again. And so what we're really trying to think about is how we can develop learning-based systems for this competition, but that they can be robust enough that you can just kind of put the robot out there, take your hands off of it, and trust that it's going to perform well. So we've been working in this domain as a challenge task for reinforcement learning. And I want to tell you about this as a case study of what we've done and what the lessons are for how we can apply RL in other contexts. So the overall approach here, right, is that we have a robot. The robot has some sensors on it. So in this case, we're using the Now robot for the particular competition we're using. It has two cameras in the head, has a number of other sensors like proprioceptive sensors. It can communicate with other robots, and IMUs, kind of some standard robot sensing capabilities. And then, of course, it has a number of actuators. So it's got 25 degrees of freedom. Not all of them are important for playing soccer, but a lot of them are. So, ultimately, you need to control those. So this is a very, you could think one approach is, well, maybe I'll just try to go end to end. I'll learn one big neural network, which maps from these sensors to the commands. But that's going to be really challenging to do and really challenging to train, and kind of particularly when you care about robustness. So one of our first steps here is to say, well, actually, there's a lot of really good robotics techniques that can make this. We can scope the problem to make it appropriate for reinforcement learning to do well and deliver robust control. So there's a number of good, approaches for real-time perception, fast neural networks that we can use for object detection, and there's also really great techniques available for localization, variants at different variants of filters. We don't really have to worry so much about mapping in this domain because you kind of already know what the landmarks are on the field and where they are in relation. And then, of course, after you've constructed this high-level state estimation, what's really actually kind of tricky to specify in this domain is the higher level decision making. Like, what exactly are the right the behaviors that the robot needs to engage in for both the multi-agent coordination as well as the single agent strategic behaviors in the presence of opponents. Another thing where you might think RL is a really good fit in this case would be motion control. There's certainly a lot of work, including some of my past work on, in this domain about thinking about how we can, get robots to walk faster or get up off the ground faster, things like that. In that case, we haven't focused too much upon it because of, I think, really the existing kind of controllers based on, other approaches, non-learning approaches are really kind of at the maximum level on this robot. So there wasn't like a lot of gain to look into reinforcement learning here. But where we did think there was a lot of potential was how can we learn these high-level behaviors here. And so we've done work in both multi-agent reinforcement learning and single-agent learning. I'm going to mainly focus on the single-agent part here, and that's what we've used when using this competitively. So I'm going to talk about how we can learn high-level strategic behaviors for just a single robot to follow. I think the first challenge here is that so soccer is a very complex task, and so just trying to learn kind of one single neural network that does everything can be very, very challenging. And you often find that there's one approach will work for some situations, and another approach is useful. So what we kind of finally settled on is that we need some sort of decision-making architecture that officially is going to efficiently route between different behaviors. So what we've developed in our system is that we have some type of behavior selection policy which handles this routing. And then depending on the particular situation, a different learned policy is called. And one of the really kind of important reasons for doing these, having separate policies, is that you find for different subtasks within the domain, even the definition of the reinforcement learning problem can change. So what are the important features to pack into what the policy observes? What is the right control space? So all of this can change across different subtasks in the domain. And so having this kind of this modular architecture was really important for doing well there. Now, this is the overall behavior architecture. But we still are faced with the fact that we have a domain for which it's very expensive to collect experience on any of these subtasks, like setting up different like kind of little soccer games to generate experience would be impractical. So we do what many people do, and we take a sim to real approach to learning each of these individual policies. But perhaps what's unique about what we're doing is that we've really kind of embraced multi-fidelity sim to real. And one big kind of guiding question for this work has been, how exactly realistic does simulation have to be in order for us to get effective sim to real transfer? And so what we found is that because we're just focusing on these high-level behaviors and we're relying on existing components of the classical robotic stack to generate good state estimation, as well as providing a higher level interface for control, we can actually get away with using highly abstract simulations. So we do a lot of, in our base simulator that we did a lot of this work, we have a very coarse abstraction, a very coarse representation of these games. This makes the simulator very lightweight, so we can train policies very quickly. And one other advantage of that is that we can generate like very diverse situations. And this really helps with robustness. Like if you're not kind of effectively covering the space of all sort of possibilities that the robot might find itself in, then you don't get behaviors that generalize well across the whole any situation they might end up in. So once we've applied this approach and we've learned policies in this abstract simulator, we transfer them onto the robot. And this is for about like 75% of the behaviors that we're running. This approach suffices, where we're just taking advantage of existing pieces of the robotic stack to make the problem, to essentially simplify the problem and just use reinforcement learning at that high level. Now, this doesn't always work. Again, the question is, how realistic does simulation have to be? So there's some other situations where you find where you actually need some, more like a higher fidelity simulator to learn the right behavior. So particularly close to the goal line, we really care about the efficiency of the robot getting the ball across. And so that was one case where we would always use kind of high fidelity simulation to learn those behaviors. This wasn't something that we've used within the competition, but we've also done some work on multi-agent reinforcement learning in these like really abstract simulators and looked into the techniques. So this is from an ICRA paper last year, where we were showing, what are the ways if you wanted to do multi-agent RL, sim to real, how you could do this with a really abstract simulator for simulating team play. And so we showed that we were able to do this, and it was better than just like the single agent RL approaches on these tasks that really required coordination. And in fact, we even benchmarked it against the team that won the RoboCup competition, and showed that we were able to start kind of closing the gap with learned behaviors there. One So one thing that I think is really important in this work, but is something that has kind of been driven home for me as I've looked at a lot of different like applied RL works as well as experience in other domains, is that we don't necessarily in the field talk enough about RL environment design. So RL problems are typically modeled as Markov decision processes, and I think the ultimate goal of the field of RL might be that we don't have to think too much about that design decision, that you could just like be given a MDP and then good enough RL algorithms would solve it. But in practice, the task MDP has to be designed just as much as the learning algorithm does itself. So these are questions like, how do we define the state space? What are the actions available to the agent? And what is the reward? Now, there's a lot of discussion in the literature about how do we define reward functions, but I think also these questions about what are the states, what are the actions, and there's some other considerations too. They're kind of just as important. And they often that's what you spend a lot of time iterating on in practical RL is just how do you set up this MDP correctly. So in our case, we found that it was critical to kind of use different instantiations for different sub-policies that we were looking at. And the two main considerations that we're looking at here are one, learnability. Like I need to set up an MDP that existing RL algorithms can solve. And then also we have this consideration of sim to real transfer. So sometimes there's cases where you want to make your simulator even like a little unrealistic in certain ways, because this will encourage robust behaviors that transfer better. And so there's different considerations like this are really important in practical RL. Just to give one kind of result highlighting that. So this was, we were looking at developing a behavior at how the robot can dribble around opponents. So if you watch the video, you can see one example of this, whereas this is our robot has the ball and is going to try to dribble around. So that's what success would look like in that case. And what we spent time thinking about is like, what is the right control space that the robot should be using in this case? So we had a couple of different high-level control schemes. One was that the policy could output a desired relative speed for the robot to move. And the other possibility was that the robot could walk to a desired point on the field. So walk to point was a really good action space on some other subtasks, like when we needed the robot to position in certain places, but it was really bad for this particular situation. You can kind of see that in the results that I'm showing here, that both in like real and simulated evaluation, it worked a lot better to choose the control space to be walking at this relative speed. Yeah. The last kind of big lesson I would highlight from this work is that there's in many cases, you already kind of know what the right behavior to do is. And it's always kind of tempting to try to do everything with reinforcement learning. But oftentimes a little human knowledge will really go a long way. And if you know what your agent should do in a particular situation, it almost always makes more sense to program that in explicitly rather than to try to learn it. So here's one instance of this that I really liked from the competition in 2024, where we've been awarded a corner kick. And you see that robot 4 in the middle has positioned itself appropriately. That was a very manually specified set play that we're running there for exactly that situation. Of course, you could imagine that if you did enough multi-agent reinforcement learning in simulation, that kind of behavior might emerge. However, it's just a lot easier to say, we know what should happen. Let's program that in exactly. This gets to the end of this first part of the talk. I think the main takeaways from it is that I do think that ultimately the goal of the field of reinforcement learning and in robot learning, the goal should be to develop algorithms that can learn optimal decision making with really minimal additional system components added. So I completely agree. I think the end-to-end vision of learning is a really great view. But I also think that doing so is going to be intractable in many real-world problems that we have today if we're using today's learning algorithms. But there can still be tremendous value in using RL in such domains, but it requires scoping the problem correctly. So understanding, what are the factors that make RL work well, what makes it work poorly, and what available domain knowledge can be used to prop up training such that we can be successful. And I think when people, spend time to do that, and this is seen in a lot of big success stories of RL. There's a lot of a lot of work, particularly if you read the appendices of these papers on doing exactly this. And then you'll find that we have algorithms that often really work well in practice today. And so I think that's tremendously exciting that our algorithms can be having real world impact today, even as we kind of move towards this longer term vision of being able to learn everything in the system. Yeah. So
Yeah, do you mind if I ask a quick question, Josiah?
yeah, yeah, please. I'll pause here and then I'm gonna move on to the next part. So I'd be happy to take questions now.
Great, yeah, and hey, Glenn, by the way, good to hear you talk about some
Oh,
stuff in research and get
yeah.
to chat. So I was wondering here for the end-to-end part, because at least in a chunk of the robotics community, the end-to-end is looking a lot more imitation learning like than it is RL like. So maybe if I can ask you like to go a bit deeper into like, so do you see maybe an end-to-end future that's just straight RL, or do you think you'll have to put in a phase here that's a lot of imitation learning before getting to end-to-end RL? What do you think?
Yeah, sure. Yeah, it's a great question. I mean, as long as we're talking about the distant future of the field, right? And we're not sure exactly how long it takes. Um, I think systems that learn end to end without demonstrations are going to, kind of be viable in some way. Now, maybe I will just the caveat here is like, is that being learned purely from reward? Is there some reward and that's the only learning signal? Um, I guess I'm more skeptical about that, and that I think there's a really important role for types of self-supervised learning, for building up just good predictive knowledge of the world, like model learning, techniques like that. But like I do think eventually, we will get to the point where we can develop agents that learn without demonstrations of what action to take in situations. Yeah. Um,
I had a
Okay, thank you.
question.
So it's mostly looking at it. We shouldn't need to have the fixed data that needs to be provided by an expert, but there'll be some important data generating process, hopefully through RL.
yeah. I mean, of course, this is all, I guess it's, I think imitation learning is a very pragmatic technique. And, why kind of search every possibility? Like if you have some task that, you care about solving and you have some basis of knowing what good actions are, I think it makes a lot of sense to start with it. But I think we like as the field of reinforcement learning for really kind of understanding principles of intelligence, that we also need to think about how we can get away from that. Particularly, I think the case of like where you have explicit action labels provided to the agent. Now, I think learning from observation is a really important capability. Yeah,
Okay, great. Thanks.
yeah. I mean, that's obviously my very like kind of speculative research bet question how things will go. I'm sure that there can be lots of debate about it.
Mhm.
Yeah. Any other questions before I continue?
I had one. I was just wondering if you could um, be a bit more precise about what the state representation was in the single robot case.
Yeah, yeah, sure. So we're basically using, right. So higher, I guess, like a higher level description of the task setting. So like where am I? Where are robots around me? Where is the ball? So kind of like exactly like you'd think like object positions. Um, a little bit of, and I would not be able to be really precise about this now. I can say that it does. My students have found that it matters exactly how you encode that information. So sometimes, specifying things in terms of like the relative frame versus global coordinates can really make RL work a lot better. But in general, it's, kind of where are the key objects.
Awesome. Thanks.
All right. Then I'll move on. So the next thing I want to talk about is how can we trust learned decisions? And so one of I think the big questions here in reinforcement learning for doing it when we're trying to apply it is we would like to have some confidence that these learned decisions are not going to have too bad of real world consequences. So There's many different ways of looking at safety and reinforcement learning. The particular question that I'm going to talk about is, can we determine the expected performance of a learned policy before it's deployed and actions have consequences? So I think this is really is one of the most basic questions for RL, because in reinforcement learning, we care about maximizing expected performance. So we might as just a first cut at safety, want to be able to say, I would like to know what the expected performance of a learned policy is going to be before it's deployed. One of the techniques that myself and many people in the community have looked at for this problem is offline evaluation. So how can we use historical data, perhaps collected from other agents on the task, or even human decisions, and what is the effect that they had in the past? Can we use that to predict how a untested policy is going to perform? So in this context, when I say data, what I mean is kind of the basic building block of data in RL is the transition tuple. So we get state, action, the reward that followed, and what was the next state that followed that action as well. So what we're trying to move towards here is that we would like to say, okay, we're in a setting where there's data that is collected from some existing deployed autonomous system. We can collect that data over time, and now say when we get any sort of new and untested policy, we have a set of methods that we call offline policy evaluation, or OPE methods. And then these methods would allow us to make a decision about whether we should deploy that new policy or not. And the way they're going to work is they're going to try to predict what is the expected performance of the new policy. And then we can say thumbs up or thumbs down based on how if that's a significant enough performance improvement. There's a lot of use cases for this. So a lot of work has been done on OPE for personalized medicine, where you have data from doctors, and you want to really validate performance of a policy before allowing it to prescribe treatments for a patient. There's been some work on autonomous driving. Certainly a lot of work on model-based approaches to this through world models are beginning to emerge in autonomous driving. And then really kind of automated investing as well. In general, any domain where we have instances of past decisions and outcomes and a new policy to test, this is where these methods can be used here. So to be a bit more precise about the problem, we're given a policy, pi, and a data set, which consisting of these transition tuples. And our goal is we want to be able to estimate the expected cumulative discounted reward obtained when running policy pi here. So this is just a formal statement of it. The key thing which makes this problem interesting is that the actions in this data set were going to be taken by one or possibly more policies that were different than the policy that we are trying to evaluate here. So what's hard about this problem? Well, effectively, the problem is distribution shift. So this is a really simplistic toy environment that is designed to just illustrate this problem. So we have 4 possible states, and there's only one state where there's a decision to be made. That's to go up or down. We're trying to evaluate a policy that will go up with probability, 0.99, but the policy that generated the data would only go up 1% of the time. And the effect of this is that our data is going to mainly consist of these down actions, which aren't as relevant to evaluating the evaluation policy. It gives us a really high distribution shift between what the data would look like under the evaluation policy versus the behavior policy here. So that's distribution shift right. So we can see what we're going to end up with is that we're going to see state 2 much less frequently than we would in our data than we would if we had actually ran this evaluation policy that we're trying to evaluate here. Now, this example, though, is also designed in a particular way to illustrate what an opportunity for improving these kind of methods and actually eliminating this distribution shifts problem. So if you look closely at the setup, you can see that in either states 2 or 3, the reward is going to be +1 for the agent, and then the agent is going to transition into state 4 here. So what this means is that you could instead view states 2 or 3 as really belonging to just kind of being essentially the same state, saying that it doesn't matter what the agent does in the first state. It's going to transition into this middle region where it's going to receive +1 and then transition into +4. And what this is trying to illustrate is that there's an opportunity to actually eliminate distribution shift if we can find the right representation of states in our data here. And so this has motivated a line of work in my lab on how ideas from the abstraction literature and reinforcement learning, as well as representation learning, can be used to make these offline policy evaluation methods scale up to more interesting problems, with robotics being one of the main motivators for that. So just to add a little bit of context, there's been substantial work in OPE in recent years. A lot of this focuses, though, on statistical efficiency of estimators. So at designing new techniques, such as using control variates or different variants of importance sampling to make these methods more data efficient. There's been a lot of work on relaxing assumptions, and then a lot of really interesting applications, particularly in healthcare, web marketing, and education. But a lot of this prior work is assumed that we just are given a fixed MDP representation. So we, in particular, some fixed representation of the agent states and actions and what the reward is, and said, how can we solve the problem with that fixed representation? So now calling back to the first part of the talk, I'm saying how that is set up really matters a whole lot. But what we would like to do is we would like to try to learn what is the right representation to make offline evaluation tractable. So in the first work in this space, we were just tried to ask this question of, could abstraction help? So we first looked at, okay, given a particular state abstraction function, which is going to, ignore different kind of irrelevant differences between states to try to, give us a good representation. How can we, does this actually help offline policy evaluation? So in this work, we showed, this was a AAAI paper from a few years ago. We showed that yes, if we kind of had the right representation of the data, it could make a big difference. So just to understand this result, the y-axis is relative error. So we want that to be as small as possible. And the batch size is how much data is available. So the ideal is to get as little error with as little data as possible. And we're just showing this is a Mujoko control task that if we apply the right abstraction to the data set, then we can get a lot less error. So this was a proof of concept that this idea of if we wanted to have really good OPE, it really mattered what the abstraction was. But the biggest limitation of the work was that we don't necessarily know what the right representation is a priori here. So this motivated us to look into methods for learning representations in reinforcement learning, and particularly methods which are based on the concept of state abstraction. So in state abstraction, the idea is that we want to try to group states together such that the differences which are relevant for predicting expected future return that's used to differentiate states, but irrelevant differences are kind of discarded. So if two states only differ in some features that aren't relevant for predicting expected future return, we can just kind of treat them as essentially the same state. So in this work, we defined a distance metric, and we actually do this not on top of states, but actually state action tuples. So we want to say how kind of behaviorally distinct are two different state action pairs. So you can define this in terms of two components. One is how distinct are these state action pairs in terms of the immediate reward that you would get from them. And then also what is kind of the longer term expected future difference between them as well. So I'm happy I won't go into any more detail than that, other than to say that we define this distance metric in our work. And then what we want to do with it is to say that we're going to embed state action pairs in some vector space, such that the distance in this embedding space is going to match this distance metric, which we've defined. Just to describe to illustrate what that looks like here. So this is showing each state action pair has a vector representation. There's going to be some naive state action feature space, which is given to you. And what's being shown in green is these are state action pairs that have the same action value. So the same future expected discounted reward from them. So that's green, and then blue is kind of the same. So that's X2 and X3 have the same action value as well. And there isn't any relationship between the color here and the direction that's being, these native features are pointing in here. So our goal is that we're trying to learn an encoder which maps these features into a new embedding space. And so once we do that, we want it to be such that if two state action pairs have really similar action values, we want them to kind of share a representation. And so that's what we do with our method rope. And we show that, we're able to do this, so that now we're kind of aligning, if they've got the same action value, they should be kind of closer in this space that they get to. And so this is giving us, intuitively, it's giving us a representation which is going to discard the irrelevant problem features or irrelevant state action features, and allow us to do more, to have more accurate offline policy evaluation. So the total approach here is that what we're going to do is that we first, when we're given this fixed offline data set, do a representation pre-training phase, which allows us to determine what are like the right way to represent state actions in our data. And then we feed this into just an existing off-the-shelf offline policy evaluation phase. And what we're going to find is that this is going to enable us to do more accurate policy evaluation. So just to show that, we have some empirical analysis. So first, we're looking at a bunch of these different offline data sets, offline RL data sets, which have been put out there on continuous control task. And we see that we get a lot less, we get lower OPE error, so more accurate prediction. Another important property is that we want to be really robust across hyperparameters. This is really particularly important in OPE because you often don't have access to a ground truth value for tuning your hyperparameters like you might in other RL settings. And one other kind of final result is that we see that our method is a lot more stable. So if you're familiar with like some basic like kind of fundamentals of off-policy reinforcement learning, you know that off-policy reinforcement learning in some context, when you use function approximation, leads to divergence. But we're actually showing that we're able to learn a representation that is making us more robust, and so not diverging in these contexts. So that was an empirical finding we had. So we followed this up with some other work that was at ICML this past year, where we actually we kind of modified our representation learning procedure a little bit, and we're able to show that we had theoretical guarantees that our offline policy evaluation methods would not diverge. And as well as kind of empirically looking again at more of these offline RL data sets, that we're getting even lower error, more accurate evaluation, while still making sure that we don't diverge in practice. Yeah. So main kind of takeaways from this part here, I think that offline policy evaluation is one of the kind of most crucial areas of reinforcement learning work, in the sense that we do really need to know how do you go to a domain stakeholder and say, I've developed this great reinforcement learning policy. How can, let me tell you that it's going to be performant. It's not going to, cost you money or lead to some potentially bad consequence. Like, we need methods for that problem. I think today's methods for OPE don't really scale to very complex robotics tasks. We're kind of working on some benchmarking efforts right now on trying to really understand what the pain points are for things like manipulation and autonomous driving. But I do think that one of the critical pieces to enabling OPE in robotics context is like figuring out what is the right representation for the problem. And so we've really focused on this by looking at how we can abstract away irrelevant problem features through a framework of state abstraction, and we're showing that that's a promising direction for scaling up OPE. Yeah. Okay. So yeah, please.
Thank you. That was pretty interesting. I had a quick question about kind of related to like the hyperparameter robustness. Are you ever able to tell like it's good essentially if you, without like having to do a real world evaluation, or like seeing like how well the like open method kind of calibrates with like the real world results, are you able to like ever kind of have like do some kind of like second order evaluation problem where you can like reliably tell offline when your evaluator is kind of being robust, or is that still something that that's like kind of an ongoing question?
Yeah, so I guess the short answer is it's an ongoing question. There is work in that space, it's not something that we've worked on. We typically have followed the pattern of like just saying, okay, you get to, for the purpose of the research, we determine a ground truth value in simulation and see how close we can get to it. Or sometimes other works look at just like, if you have a few different policies, can your method order their performance the correct way? Yeah, but there has been some work. So I guess the person who comes to mind who's worked on this problem is Nanjiang at UIUC. And so there's some different methods for saying, okay, if I've learned a couple of different action value functions offline, can I determine which one is, going to give me the better estimate of the online performance? Yeah. I guess in short, it's an active area of research. Okay, so are there any other questions before I get to the final part here? All right, I think I'm pretty close to time, but I want to at least give like a little, a few details on this work. So this is just a newer direction in the group. So one thing problem which has interested me for a long time is this balance between, how agents can, how can they sometimes engage more computational resources to solve hard problems versus, balancing that with the demands of actually acting in the real world, which often has, real-time demands there. So I think probably many of you are very familiar with this idea of dual process theory, or the more popular notion of thinking fast and slow. So we have our system one, lazy, fast, biased decision making, great when you have real time constraints. We also have system two. It's effortful, it's slow, but maybe gives you a better decision. And there's various techniques in AI which can kind of look a bit like system one versus system two. So like our kind of typical, pattern matching ML is very system one like. System two is, a lot more like, say, our decision time planning, like in AlphaGo. So I think a really, important question for developing AI agents that operate in the real world is, how do we integrate both capabilities here? I'll go over this just so this work is very motivated by what we're kind of seeing today, though, with large language models, where people are just using reinforcement learning to try to engage reasoning capabilities in these models. So, I was kind of first aware of this with this DeepSeek R1 approach. And what really kind of struck me about this work is that if you look at this from just like kind of a pure RL perspective, where the action space here is the tokens output by the model, and eventually there's a reward for answering a user prompt correctly. A lot of the actions which are output by the model are useless from an RL point of view. Like they don't actually contribute to the reward. The reward comes for answering the prompt correctly, but all of this, so-called reasoning, these reasoning outputs, they don't actually directly contribute to the reward. And I wanted to understand, like why should these emerge? And so what myself and my student Nicholas kind of settled on here was this notion that we need to understand thinking as a form of action in AI agents. And so we're going to formalize the notion of thinking in RL agents as actions that neither produce reward, but don't or change the external environment state. So this is a really general notion of what it means to think. It's not necessarily logical, rule-based, or from explicit decision time search, although, say decision time search could be a special case of this. And we wanted to understand, like, if you formalize thinking in this way, what are the conditions under which it's going to be useful to an agent? So specifically, our question was, under what conditions will model free RL give rise to thinking as a strategy for reward maximization here? So in order to kind of rigorously study this question, we've recently, so this was a paper presented at NeurIPS earlier this month. We developed a framework that we call the Thought MDP. It's an augmentation of the standard MDP formalism, but we say that the agent now is going to have an internal state, just like the environment has a state. We're going to call this the thought state of the agent. And we're also going to give the agent a set of so-called thought actions, which enable the agent to manipulate its own internal state. Now, the limitation of the thought actions is that while they can change the thought state of the agent, they don't affect the external world and they don't produce reward for the agent. And so the agent's policy is now going to be defined as this mapping from both its internal state and the environment state to a decision about should it take a action to manipulate its own internal state or an action to manipulate the external world. The objective is the same. The agent just wants to maximize expected return in this case. Yeah. So now our question was, would an agent actually ever select the thought actions here? And one thing that you're able to show with this framework is that no, that actually a optimal agent will never take a thought action in this case. I'll skip over the proof idea here. It's fairly straightforward to show, but essentially these thought actions, if they're not producing reward for the agent, there isn't a reason for reinforcement learning to select for such actions here. Okay. But it still left us with the question of, okay, well, why do we see we argue in the work that this is a adequate model of thinking in large reasoning models. So then if thinking is not a optimal behavior, we want to know when would reinforcement learning lead to producing thinking behavior. So what we show, both theoretically and with a kind of simple example that I'm going to go into here, is that thinking can enable an agent to access useful sub-policies. And this is useful when the agent's behavior is still suboptimal here. So to give you an example of this, I'm showing, just illustrating a kind of simple domain where along the horizontal axis here, this is the environment state of the agent. And along the vertical axis, we're illustrating the thought state of the agent. We initialize this environment in a particular way such that when the agent is in the bottom row in a particular thought state, it has the worst possible thought conditioned policy that just moves it away from the goal. But if it first changes its thought state, it accesses the optimal policy that moves it right to the goal. And so what we can then show is that if we apply policy iteration, so exact policy iteration, not a learning method here, then what's going to happen is that in most of the states in the bottom row, what the agent discovers to do is that it should first change its thought state. It should manipulate that inner state because that's going to allow it to access this kind of better environment policy that's going to take it directly to the goal here. The only place where this doesn't happen is when the agent is in the environment state right before the goal, when it then just will execute the optimal action to move it directly to the goal. As you apply more iterations of policy iteration, this propagates backward to where as states get progressively, the closer states are to the goal, the more likely the agent is to just directly act rather than stopping and thinking first. And then finally, at convergence, thinking completely goes away because the optimal behavior should never think here. So this is showing why, applying some sort of actions which do not directly affect the external world can still be useful to an RL agent here. But what's I particularly want to emphasize here is that this is arguing for showing how thinking can be important, but it's completely abstracting away language from the problem. So a lot of times in these large reasoning models, the language outputs, they look like thoughts that a person could be having. Right, and so it's very easy to anthropomorphize them as as actually thinking, and to say, well, that's the reasoning chain that the model is going through to arrive at its conclusion. And of course, there's work which has shown that that's definitely not the case. But I think this is so. What our work is really trying to get at is trying to explain, well, what is the utility from a reinforcement learning point of view of those behaviors? And so this model is trying to capture that. I think it's particularly exciting in that I think what is being shown in this, what people are doing with large reasoning models is a kind of fundamentally new way of developing artificial dual process theory in AI agents. So we're casting this the idea of deliberation, like employing computation at decision time, as just a type of action that the agent can select from, just like it can take actions to affect its external environment. And now this notion of system one and system two are really now a spectrum where system two is just how much thought actions does the agent take before it finally takes an environment actions. Skip over some of the strengths of that as well as the, well, I guess one limitation I want to highlight of what we've done so far, but which I also think is a great opportunity for future work, is that in our current model, we're assuming that the world just freezes for the agent while it thinks, and that's true in large reasoning models. So it's adequate for that setting. But what I'm kind of really excited to explore is, how do we put these kind of models in agents that are, embodied in real-time dynamic environments? So now the world does not just like freeze while the agent deliberates, but deliberation actually requires the agent to kind of reason about how much might the world change, or might I need to act fast now because something bad is going to happen if I don't? So I think there's some really exciting questions to look at there. Just, really quickly, we also did some work developing kind of some non-language instances of thinking, and made some hypotheses about how, when a RL agent will choose to learn to take these actions that don't directly affect the external environment. So we developed in our work a grid world environment where thinking emerges through just applying model-free RL. I'm happy to answer questions, or you can check out the paper, but I won't talk in detail about that right now. So just to conclude, what we did in this work is that we introduced a new model of deliberative thinking for AI agents. And in this model, we're saying that an agent thinks when it is manipulating its own internal state rather than the external world. And it's doing this so that eventually, when it does take an external environment action, it's going to take a better one in that case. So we use this model to explain both theoretically and empirically how model-free RL could lead to reasoning behavior in LLMs. But I think more importantly, this is a model of how RL can be used not just to control the external environment, but also to control the computation that's used within decision making. And I think this is just another really important direction for future research. So in summary, the things I talked about, first, RL can work, but when the problem is well scoped is the current state of things right now. As we get RL working on more and more real problems, we really need tools that can predict the performance of RL agents before their decisions have real world consequences. And so OPE is one approach for this. And then finally, the last thing is that RL agents should also reason about their computation per decision, as well as, what is the value of actions that might not affect the external world, but might affect the internal state of the agent. And so studying thinking as a form of action is a promising path to building such agents. So with that, let me thank you all once again. I really appreciate the opportunity to share my work with you, and I'm happy to take questions now. And if there's not time for your question, feel free to reach out to me by email or check out more of our work at my website. So thank you.
I had a question, if I may.
Yeah.
So, in the context of the last part that you were talking about, in particular, the thinking about how long to think question, Glenn and I have been investigating this real-time RL formulation. Are you familiar with this? It seems like this idea could fit into that framework.
Okay, so I want to say I've maybe seen some of this work, or I've seen a paper from you all on this, but I don't think I think I'd have to refresh myself on the details. But yeah, it's
the most well-known
yeah.
paper, I think, was from a colleague at Mila, Chris, and I guess the idea, like, from a robotic standpoint, I think it's always bothered me that, like, RL is kind of breaking the arrow of causality in some sense. Like, you're assuming that you're getting instantaneous information back from the environment, but you're also assuming that the environment is not moving while you're thinking. And so
Sure. Yeah.
You can think about the actual, like, graphical model that gets induced and actually changing the arrows so that they correctly capture the fact that there is a latency or like a delta t that is induced.
Right.
And so now I could think about, like, doing this reasoning over that delta t thing. Like, if that delta t now becomes like part of your action space, then it could be interesting. It could be interesting to think about. I'll shoot you the paper that's sort of the one kind of like most foundational, and if you find that an interesting framework, then I'd be happy to discuss further, because we're thinking about this quite actively.
Yeah. Thank you. I'd appreciate that. I think so. As we started looking at this, I mean, this is like a really general space, right? It's like, how do you balance, like, more deliberative techniques for more reactive techniques? And there's like a lot of different instantiations of this and different ways people have looked at it, and we've really been trying to categorize them. I have another student not involved with this work, but who's starting to explore this space, and we're trying to survey a lot of it. So that would be really great to look at more as well.
Awesome.
Do we have any additional questions for the people online? All right, I think that maybe wraps up everybody's questions. Thank you, Josiah, for joining us.
Yeah, thanks so much. It was great.
Okay, yeah. Thank you all, and yeah, happy holidays. Good winter break to everybody.
Same.
Thank you.
Yeah, bye.